Hello class and welcome to lesson 5.6 hypergeometric distribution. Now hopefully you've taken a little break in the mid-chapter review, and from the mid-chapter review you examined just expected value, and then we took a look at two specific cases where we had bimodal distribution and geometric distribution. So today we're going to learn when to identify what is called hypergeometric distribution and how you can determine the expected values of that as well. Okay, so what does it mean when we talk about hypergeometric distributions? Is a fancy way of saying random selections without replacement. So if we're picking cards and we're not replacing those cards each time, then guess what's happening? The probabilities are changing each time. Okay, and if the probabilities are changing each time, that means that they're not independent and the probabilities are not the same for each trial. Okay, we still think of successes though, okay, but I want you to make sure you bubble or underline that these experiments are not independent and the probabilities are not the same. So what does that mean? That means P changes. And that's why we took a break in the midterm review. Okay? All right. So let's take a look at an example here. When drawing a card, what is the probability distribution for the number of aces in a 5-card hand? Okay, well, first of all, what's our random variable? Our random variable is the number of aces. Okay, so our success is getting an ace. Okay. All right. So what do we know? We know in 5 cards hand, you could get, oh, sorry, that's the next. You could get 0, none aces, right? So you can get 0 aces, you can get 1, you can get 2, you can get 3, or you can get 4 aces. You're pretty lucky if you get 4 aces. Okay, so how do we figure out the probabilities? Well, let's take a look. Probability, this is rough work here, by the way. And we'll put our stuff down here. So this is rough work. Do a little margin here. Okay, so if we want to do probability where the probability where x equals 0, meaning I get no aces. Okay, remember that's the number of A over the number in our sample. Okay, so if we try to get no aces, that means out of 4, I'm choosing 0, right? Which means how many cards are left over that are non-ace cards? Well, 52 is in a deck, subtract the 4 is 48. Okay, all right. Timesing by any, so 52 cards in the deck, and we're going to choose 5 of them. Okay, so just remember that there's 4 aces. Okay, and we're choosing none of them. Okay, and the 48 represents the non-aces, ace cards. Okay, all right. So plug that in your calculator, folks, and we're going to get 0.6588, and we'll put that in here as 65.88%. Okay. Let's take a look at the probability when x equals 1. Okay, so if x equals 1, that means out of 4 cards, we're going to choose 1 of them, times the non-ace cards. If we have 1 ace, that means we have 4 non-ace cards. Okay, and that's over 52, choose 5. Okay, plug that in your calculator, and you're going to get 0.2995, which means 29.95%. Okay, let's take a look at doing the next one. Probability when x equals 2. Okay, so 4, choose 2 aces this time, times 48. And how many cards do I have left over? If I choose 2, then I've got 3 that are non-aces. All divided by 52, choose 5. Plug that in, and you will get 0.0399. Notice the more aces we get, the lower this percentage is. So this is 3.99%, just to get 2 aces. Okay, so we're going to do a little bit more work here to get the 3 and the 4 and then put it in there. So when x equals 3, again out of 4, you're choosing 3, which is very, very tough to do in a 5-hand draw. Okay, we have 48 non-aces, and in that case, we're going to be choosing 2 that are non-aces, all divided by 52. Choose 5. Okay, plug it in, and you're going to get 0.0017, which means when we put in our chart, it's 0.17%, and that's only 3 aces, guys. Imagine trying to get a hand with 4 aces. Okay, what is this going to equal? So 4, choose 4. You get 4 aces, which means there's 1 card that's not an ace, right? All divided by 52, choose 5. And we got lots of decimals here. So 0.00000185, which really represents 0.02%. Okay? So it says, what is the probability distribution? Okay, so that is the probability distribution, and I'll just quickly do it on a graph, which should be down here. Okay, so we're going to do probability of aces as a nice title, or probability of getting an ace is fine. Okay, all right, and on the side, we're going to do probability related to x, and in this case, we're going to do it as a what? Percent. Okay, and on the bottom we have our random variable, which is x, which represents the number of aces. Alright, so we could have, I'm going to split this out, 1, 2, 3, 4. We can have 0 aces, 1, 2, 3, 4. 1 ace, 1, 2, 3, 4, 2 ace, 1, 2, 3, 4, 3 ace, 1, 2, 3, 4. Gonna have 4 aces. Okay? Alright, and our percentages, if we take a look at our chart, it goes from very small to about 65. So as long as we get 70 in there. So I'll skip every other one and go 10, 20, 30, 40, 50, 60, and 70. Okay, so when I started at was 0, my percentage was at 68%. Okay, so 0, you can do 0 as long as you put a break here, or you could have done 0 here as long as you put it on your axis. Okay, so I would choose a break here to show 0. Okay, haha. Now my, let me see. There we go. Okay, had my marker in the eraser spot, so that's why it was giving me a trick. So you could do a break and then put 0 there, or if you did 0 there, then you'd have to put it right on the data line, right? Okay, so for 0, we're at 68%, which is close to 70. Draw a nice straight line down. There's your tadpole or flagpole. At 1, it's just about 30, 29 point. Very, very, very close to 30. Okay, nice straight line there. 2 is 3.9, which is pretty small. Okay, and then 4, 3 is 0. Very, very small, and 4 is very, 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 very small. So you don't even see the pull part on it. Okay, so make sure you've got a title. Do we have a title? Yep, we're good. All right, so let's take a look now that we've learned at that example what the formula is. Okay, so like before, x is still the number of successes. Okay, but we have to remember the outcome is where the success changes from one trial to the next. Okay, so it is a distribution of dependent trials, which means the success will change. Okay, and we're still looking for either success or failure. Okay, all right, So we've changed it up a little bit in terms of when you see, so X is the number of successes. You just don't see the P and the Q in here. Okay? So A is the number of ways to be successful. So in that case, there was 4 aces, so that's why we took 4. And then the random variable X is the number of successes we are interested in. Okay? R is the number of dependent trials. So how many total we needed? We needed 5 cards. Okay? All right. And N is the total possible number of outcomes. So out of the 5 cards, how many total number did we have of cards? We had 52. Okay, and we chose 5. Okay. All right. Okay. And I want you to remember that A is like a subgroup of successes. Okay, so how many successes are there total? Okay. All right, so here's our expectation or our expected value for hypergeometric. It's R times A to the N, using the same preferences as that. Okay, apologize, just give me 1 second. I'll pause it. Well, we don't have to listen to